He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Kia ora and welcome to the Elemental Podcast from RNZ. I'm Alison Ballance.
And I'm Allan Blackman from the Auckland University of Technology.
Now this is episode 34 in our alphabetical adventure through the chemical elements, and we have finally made it to the beginning of the periodic table. Almost. We're up to helium. Now even I know that helium is the second element, and we'll be getting to number 1, hydrogen, in just 2 more episodes. Episode 36 to be precise. And these two, hydrogen and helium, sit in the top row or period, one at the far left and the other, helium, today's element, at the far right. So what's a good catchphrase to describe helium, Alan?
You could certainly say it's rare on Earth but universally abundant.
Tell me more.
It is in fact the second most abundant element in the universe. And so it makes up around about 23% of the mass of observed matter in the universe, taking into account that there is such thing as dark matter,
I was going to say.
Yes. So of the observed matter, yes, yeah, it's pretty abundant. But as we're going to see, we may in fact run out of it one day here on Earth, even though it's so abundant.
How come?
Well, the reason for that is that helium is less dense than air, and therefore it's not really held by gravity. So every time you fill up a helium balloon, most of the helium ends up in space.
What the listeners don't know is that I can't see you, so I didn't know that you had brought a prop in. Are you inhaling helium on this podcast episode, Alan?
Would I do that, Alison? Yes, in fact I am. Yes. And
Okay.
not very successfully either. Oh dear. I don't know what to say.
Okay. You could just give me the vital stats in a normal voice, Alan.
Okay, in a normal voice. Helium, elemental symbol He, atomic number 2, and it's a noble gas, which puts it in group 18.
So number 2, does that mean it's got 2 protons, 2 neutrons, 2 electrons?
Yes, indeed. Yes, well done.
I know that lots of those shells of electrons need to be 8, but I take it this one only needs 2 to make it full. So does that mean it's a nice stable element? It's
extremely stable. It's, in fact, probably some would say a quite unremarkable, possibly even boring element. So it's colourless, it is odourless, it is tasteless, it's non-toxic unless you fill yourself in a room with it. It's extremely inert, and as I think we talked about in the fluorine episode, it's probably the most unreactive element on the periodic table. As we said then, it doesn't even react with fluorine, which makes it extraordinarily unreactive. Now, having said that, people have been interested, obviously, in trying to get it to react with something.
Do they keep poking it? Oi.
Well, poking it very, very strongly chemically, in fact, or physically in this case. And what some researchers showed in 2017 was that if you pressurize a sample of sodium metal and helium to a mere 113 gigapascals, which is just over 1 million atmospheres, you can actually make a stable compound of helium, which has the formula Na2He, and that is quite remarkable.
That's a lot of pressure, though. They did that in 2017. When did we discover it?
That's a good question. Well, I often say, well, it was discovered in such and such a year. There's a difference between identification and discovery in many cases, and so the actual supposed date of discovery was 1895, and it was named helium from the Greek Helios, who was the Greek titan or god of the sun.
Oh, lovely.
But, having said that, it was first identified, in fact, in 1868. And the reason it was named after the god of the sun was that it was, in fact, identified on the sun before it was discovered on Earth. So a fellow by the name of Jules Janssen was interested in what was going on with the sun, and so he went to India in 1868 to have a look at a total solar eclipse using his fancy spectroscope. And a spectroscope is essentially something that splits visible light into its constituent colours, shall we say. What he found was a visible line in the spectrum of the sun at the total solar eclipse. So he's looking at the sun's corona, And this line didn't belong to any known element. And that very, very same year, so two English scientists, Norman Lockyer and Edward Frankland, they saw the same thing, and the latter called it helium because he was convinced that it was a metal, hence the IUM ending, that existed only on the Sun. So I said it was actually isolated in 1895, and what happened there was that a uranium-containing mineral was dissolved in acid, and a whole lot of bubbles of something came off, and that something was shown to be helium.
So that's helium made in a lab. How is helium produced outside a lab?
In fact, that is how helium is made outside the lab. It's a product, in fact, of radioactive decay, hence the uranium-containing mineral. What happens with a certain type of radioactive decay is that things called alpha particles are given off, and alpha particles are just helium nuclei, and they pick up a couple of electrons and become helium gas. So we tend to find deposits, I guess, of helium on Earth around about where natural gas fields are as well. And helium comes very, very often as a byproduct of natural gas production and processing. There's two major isotopes of helium, helium-3 and helium-4. And most helium in the universe is helium-4, and the vast majority of that was actually created during the Big Bang. And large amounts of new helium are being created by the process of nuclear fusion of hydrogen in stars.
So that's why it's so common in the universe?
Yeah, indeed, yes, yes.
What do we use it for?
Helium is of increasing importance, certainly in medicine. If any of you have ever had an MRI scan, magnetic resonance imaging scan, helium is absolutely vital for the operation of those instruments because they use what are called superconducting magnets. These are magnets that basically give very, very high magnetic fields, and they run without any input of power once they're superconducting. So the helium cools them down to very, very low temperatures, around about minus 269 degrees Celsius, which is pretty cold. And so not only in MRI spectrometers, but in a variety of scientific instruments where you need very, very cold temperatures, generally to keep these magnets superconducting. And so at CERN, where they found the Higgs boson, for example, there'll be truckloads and truckloads, literally, of liquid helium used there. And the reason that we use helium to cool things is because helium's got the lowest melting point and the lowest boiling point of all of the elements. And in fact, it's the only element that you cannot solidify at atmospheric pressure, which is kind of interesting. So that only liquefies at around about minus 269 degrees Celsius, which is in real temperature units 4 Kelvin. And if you go down to about 2 Kelvin, it becomes a thing called a superfluid, which means that it will flow out of any unsealed container in which it is placed. It just climbs up the walls and just goes everywhere. Quite remarkable stuff.
Now, staying with the theme, climbing up the walls, you did allude earlier to the fact that we use it a lot in balloons. You know, it's got lightness, it's got lift to it. Is that useful for us?
Oh, very much so. More than just party balloons. So it was used in airships way back in the first 3 or 4 decades, I guess, of the 20th century. And they are just really, really big balloons.
Indeed.
Any of you who go diving will well know that you use a helium-oxygen mix in diving gas mixtures. The reason being is that helium is less soluble in blood than is nitrogen, and nitrogen also gives you a narcotic effect, which helium doesn't give you. So that's all good. And it's used as an inert atmosphere in industrial processes, such as things like growing crystals to make silicon wafers, for example.
Now, helium sometimes does make news headlines. I'm thinking, you know, those scary headlines. Prices going up. World supply of helium about to run out. Is this true?
Well, that sort of depends who you talk to, I guess. So, for example, each year, the world roughly uses around about 175 million cubic metres of helium, which does sound like rather a lot.
That's a lot of party balloons.
Actually, it'd be interesting to know just how much of that is party balloons, to tell you the truth. So there is a little bit of concern that we are going to run out of helium. It is a non-renewable resource, so certainly one day we will. But in terms of a reserve, it's estimated there's around about 28 billion cubic metres of helium currently that we have yet to mine, as it were. And the gas industry reckons that at the current rate of production, and you allow for conservative growth rates, we're okay for decades, for the moment anyway. So for the next few decades, we're okay for helium. And obviously it is important, so people are going looking for it. And in fact, two of the largest producers of helium are in fact the United States and Qatar, of all places. In fact, since the 1920s, Amarillo, Texas, that town of the famous song, "Is This the Way to Amarillo?" Every night I've been hugging my pillow, etc., etc. Bad rhymes. You don't know that one?
I do know that one. I'm not going to try and sing it.
But apparently Amarillo is home to America's Federal Helium Reserve.
Well, that sounds really important. It sounds like the Federal Reserve Bank or something.
It does, yes. This is a massive underground geological formation and natural gas supply. And Amarillo, like many American towns, has to be the world capital of something. So it calls itself the helium capital of the world. And in fact, there's a monument to the element in the town, which is a 6-story steel spire with a model of a helium atom at its centre. Very classy for a town, I'd say. And recognising its importance, in 2018, helium was in fact added to the critical minerals list, both in the US and the EU. And the US is actively looking for ways to remain self-sufficient in helium. And I guess luckily for us, there are new helium sources that are being discovered both in the US and also Algeria, for example.
So those MRI scanners are going to keep working. That's good to know.
It is.
Interesting fact, please.
Well, helium is the second lightest element, as we've already talked about. But in 2011, scientists made a few fleeting particles of a thing called anti-helium, which is the heaviest breed of antimatter.
Anti-helium.
Anti-helium. That sounds like something out of Star Trek or whatever.
What is anti-helium and antimatter? What's that all about?
Well, it's sort of the mirror image of matter, if you want. Okay, so we know that, for example, protons in our world are positively charged and electrons are negatively charged. So that's what we would call normal matter. In antimatter, those are reversed. And so, for example, we have protons essentially that have negative charges, which we call antiprotons, and we have electrons that have positive charges, which we call anti-electrons or indeed positrons. And so what you can do is, if you're really lucky, you can then create antimatter atoms by taking these antiprotons and anti-electrons and constructing antimatter atoms out of these. Not an easy thing to do. And so these folk made 18 anti-helium atoms, and they survived for at least 10 billionths of a second before they came into contact with some matter, and when antimatter and matter get together, they, quote, vanished in the tiniest of fireballs, according to The Guardian, which is very nicely put. Now, heavy, I guess, this is the supposedly heaviest piece of antimatter, but heavy is a relative term. So anti-helium's the heaviest antimatter known, but each particle or each atom is still roughly about 10 million billion times lighter than a grain of sand. So everything's relative.
It is. So anti-helium, they say it's heavy, but that's ridiculously light. I think, Alan, we'll just stick to making a podcast about matter rather than antimatter.
That is probably wise.
Which is why you'll keep listening to Elemental the podcast and not Anti-Elemental the anti-podcast.
And we are definitely online at rnz.co.nz/chemistry, and you can find us as a podcast in all the usual places.
And I'm Allan Blackman.
And I'm Alison Balance. We're back next time with Helium. But until then, kia pai tō rā.